Here, we were looking at the pressure volume curve, and this was the very last topic in the cardiac cycle. And this is just really tying up a lot of what we already discussed individually when we talked about the cardiac cycle. So we looked at the four phases, right? And just to remind ourselves what those are here, we have phase one, which starts in the middle of diastole. So this is a filling phase. And if we think about what's happening here with this pressure volume curve, we're comparing the pressure in the left ventricle versus the volume in the left ventricle. And how are those things changing? And because we know this is a cyclical process, that is going to make a loop or a curve, right, on this graph. And it's going to happen in sort of a cyclical fashion where we fill volume, eject that, fill volume, eject, etc. So phase one is the middle of filling. And because the heart never is empty, because the ventricles are never empty, we start at 60 mLs, right, instead of 0. And we fill to about 130 mLs as our total end diastolic volume. So this is our end systolic volume, 60. This is our end diastolic volume. And this is the beginning of filling, or phase one. Then we have the isovolumetric ventricular contraction. And here, there's no change in volume, so there's no horizontal change on the curve, but there is a change in pressure. In this stage, all four valves are closed, so there's no movement or change of volumes of blood, but the pressure is rising, right? The chamber is contracting, hence the isovolumetric contraction phase. And so pressure rises until we get to phase three, which is the ejection phase. So in phase three, we're going to expect to see that the pressure goes up, all right, which you can see a rise in the pressure, but the volume goes down. So now we have this sort of backwards shape to our curve. So the volume goes from 130 back down to 60, and 70 mLs are ejected in phase three, okay? We go back to 70 mLs. From there, we have isovolumetric ventricular relaxation, which brings us back down to a zero pressure, right? Pressure drops here once again as we are relaxing the ventricle in preparation for filling phase again. So this is how the phases that we discussed are, the volume and pressure is relating during those four phases, and this creates what's called a pressure volume loop or pressure volume curve. Now, the way that we use this clinically is to tell us about the efficiency of the ventricle. This is going to be what we use to help us determine if there's any heart failure. So if you have a left ventricular failure, you're going to see the volumes get bigger, right? The heart is not ejecting blood as forcefully because the muscle is failing. That's what heart failure is. And so if it's happening on the left side, for example, the left ventricle, we're going to have more volume left in here than we typically should, because there's going to be sort of an insufficiency or regurg of blood that's staying in that chamber. You're also going to notice that the pressure is not going to be as high. So there's going to be a distortion of this loop or this curve. And it's going to be wider and shorter as pressure is not as high, but volume gets bigger. So we can look at different sort of morphologies or changes to this curve depending on issues with the heart. If we have a valve stenosis, for example, which is where this valve is not opening as it should, if it's calcified or stenotic, we're going to see higher pressures as we try to overcome that resistance. So again, this can be used clinically to help us determine the pathology happening in the heart. Let's think about the heart sounds finally. So this is where we assess the turbulence of blood flow as the valve is closing. That's what causes or produces the heart sounds. And this is how we can detect, again, the health of the heart, the cardiac cycle, the length of each phase of the cycle, and we can use that during our physical examination. So the first heart sound is a softer pitch, and it is caused by the closure of the AV valves, right? Which would make sense. This is what's going to happen when we have the ending of phase one and moving into phase two. So ending of phase one, AV valves close, right? That's after diastole. AV valves close, and as they're closing, the blood that's hitting against the back of the closing valve creates some turbulence, which is a soft lub. So the reason is the pressure that causes a back shift of blood towards the atria, and then the motion of the closing cusp of the valve. So it might be tempting to think that it's the blood moving through. It might be tempting to think that it's the valve that's clicking to cause the lub, but it's really a combination of both. It's the blood moving against the closing valve, very specific, that causes the heart sound. And then the second heart sound is a louder dup. It's a higher in pitch and it's louder, and it's caused by the semilunar valves closing. And it's usually higher because there's more peripheral resistance in the arteries that's going to hit against the closing semilunar valves. So when those semilunar valves are closing, it's a bit of a higher pressure, causing a back shift of blood towards the back of those closing valves. All right. So when we hear the heart sound, it's usually a lubbed up, so a softer, quieter lub, and then a higher pitch and louder dup. Okay. And then we also want to just make the connection here that the heart spends more time filling. So the lub is going to come in a bit later, right? Or sort of more delayed as the heart spends more time in diastole. And then the heart spends less time in systole, so that dup is going to be a bit faster than the first heart sound. Okay, the heart spends about 2/3 of the entire cardiac cycle filling so that it can adequately eject. And then just reminding ourselves here of where these heart sounds come in. So again, at the end of phase one, when the AV valves close, we have our heart sound one. At the end of phase three, or ejection, when the semilunar valves close, we have heart sound two, right? So the lub and then the dup. Okay. So let's do a few practice questions and we'll move into part four. Okay. So our fourth objective is to understand the regulation and control of the cardiac output, really putting all of this together and seeing how cardiac output is regulated. So let's talk about what cardiac output is first. It's the amount of blood pumped by each ventricle per minute. So therefore, it's a rate. And the way that we calculate that is our stroke volume times our heart rate. Okay. Another reason why it's so important for the rate of the heart to be adequate in order for us to have proper cardiac output. Now, the total number that we get is usually about 5 liters per minute at rest, which is really fascinating because our total blood volume on average is about 5.5 liters, which means that every minute at rest, your heart can mobilize your entire blood volume, which is extremely fascinating. And if you think about exertion, exercise, times of stress, this can go up even more. So the heart is one of the hardest working muscles in the body, as you probably have guessed by now, and it's essentially what's keeping you alive and keeping all of your tissues perfused adequately and nourished right as well. If you think about the factors that control the cardiac output, heart rate is one and stroke volume is the other. Now, if you look at those factors individually and think about things that control each of those variables, we can think about extrinsic factors like neurons and hormones, right? Neurotransmitters that will bind to receptors on these cells, or we could think about things that are intrinsic to the heart, like autoregulation. And we'll talk about what this is, but these are factors inside the heart that can change the heart rate or the stroke volume, such as the state of the ventricles or even how much blood has been filled. So those are going to be factors internally versus external things like hormones and neurons. Now, we want to remind ourselves of the division of the nervous system that is governing the heart. This is the autonomic division. And so it's going to have a contribution from both the sympathetic part, which is T1 to L2, right? We've talked about this specifically T1 to 4 for the heart. And then the parasympathetic division coming from the cranial nerves, which originate in the brainstem, the medulla. And this is specifically the vagus nerve, and that will give parasympathetic contribution to the heart. So the sympathetic will govern the SA nodal cells, AV nodal cells, and the contractile cells of the ventricular myocardium. However, the parasympathetic system will only influence the SA nodal cells and the AV nodal cells, right? There is no influence on the contractile cells that comes from the parasympathetic system. So the parasympathetic system only controls the rate and rhythm, whereas the sympathetic system controls the rate and rhythm and the ventricular contractility. Okay. Now we want to think about the heart rate, and let's talk about factors that can manipulate or regulate the heart rate. It is going to be determined by the firing rate of the SA nodal cells. If you think back to those autorhythmic cells of the SA node that we described earlier, the intrinsic firing rate is about 100 beats per minute. But under the influence of the parasympathetic system, that tones it down to about 75 beats per minute, okay? Another way to sort of simplify that concept is if you were to take an SA node cell, take it out of your body and put it into a petri dish in a lab somewhere, it's gonna generate an action potential, 100 of those in a minute, right? Because there's no extrinsic control on that SA nodal cell. However, in our body, under the influence of our autonomic nervous system, specifically the parasympathetic division of that, as well as hormones, that rate comes down to about 75 beats per minute, which is our resting heart rate. Okay. We also want to remind ourselves that we can have sort of a balancing act here. During periods of rest, we're at 75, but if we're excited, exercising, that can go up to 100 as well under the sympathetic influence. Okay, so let's think about the neural input here. So what are the neural inputs and what are the steps in that control heart rate? So if we're looking at the sympathetic nervous system, this is going to be the adrenergic neurons and adrenergic receptors that we discussed earlier. They're going to be specifically beta-1 receptors. Those are the specific type of adrenergic receptors that are found on the SA node. And they're going to change the state of their opening of calcium channels and sodium channels when epinephrine or norepinephrine binds to these beta-1 receptors. Okay, and you should recall the mechanism behind this. Remember, this is cyclic AMP, adenylyl cyclase. We talked about the whole signaling cascade that would actually bring about this response. The end result that we're going to see here on the cardiac SA nodes will be an increased rate of depolarization. That is, the spontaneous autorhythmic depolarization that we see is going to happen faster and more easier, and that is going to result in an increase in heart rate. All right, so this is how the neurons of the sympathetic system, right, those postganglionic neurons, by release of epinephrine and engaging our beta-1 receptors, results in a faster heart rate. Okay, let's illustrate that same concept here. So here's our neurotransmitter crossing what we refer to as the neuroeffector junction, if you remember that junction, binding to a beta-1 receptor, and then bringing about the signaling cascade events, which involve the G protein, a stimulatory G protein in this instance, the dissociating of that subunit, the amplifier enzyme being adenylyl cyclase, and then the second messenger being cyclic AMP. From there, this is where we kind of were ambiguous when we discussed this earlier, but now we're looking at the heart specifically. We can really hone in on the exact events that bring about a response on cardiac muscle or the SA nodal cells. So this is going to result in protein kinase production, increase in protein kinase, and protein kinase is going to result in our funny channels. Remember these channels that we discussed as being the main event that starts an autorhythmic or spontaneous depolarization in an SA nodal cell. And so those funny channels are going to open up. Sodium and potassium will move, more so sodium coming in, and that is going to lead to a depolarization. The other thing that kind of gets us starting this action potential here on SA nodal cells is the T-type calcium channels or the fast calcium channels. And so those two will open up, calcium can rush into the cell, and that will further depolarize the cell. So this is just kind of tying together events that we've talked about previously to show how the sympathetic system, by way of the autonomic, by way of the neurotransmitter release and the receptors here can bring about an increase in the SA nodal firing rate and an increase in the heart rate. Okay, let's look at the opposite effect, right? Still looking at the heart rate, still looking at the neural input, but now we're looking at the parasympathetic division of that. And the parasympathetic would be vagus nerve here. This would bind to muscarinic cholinergic receptors that are on the SA node. And that would result in an increase in the open state of potassium channels and the closed state of calcium channels. So now we're going to have an open state of potassium channels, which just makes it harder to depolarize the cell. Remember, potassium's movement repolarizes the cell. So if we keep potassium channels open, then it's going to be harder to get that cell to a depolarized state. So the rate of spontaneous, depolarization decreases, and the heart rate too would decrease. Okay, let's illustrate that here again. So here's our SA nodal cell. Here we're looking at the parasympathetic events. So now we're thinking about a muscarinic receptor, which is also coupled to a G protein. Acetylcholine will bind to that receptor, and we have two types of events that decrease the heart rate. One is closing of calcium channels. So now it's harder to depolarize the cell. Okay, and the other is opening up potassium channels. So now potassium's leaving. So again, it's harder and less favorable to depolarize because this is going to hyperpolarize the cell. So now this is how we decrease the rate of spontaneous firing of these cells, and then we decrease the heart rate. Okay, and just to compare all of those three effects, at rest, we have a standard rate of firing for the SA nodal cells. So let's say in this time span, the SA nodal cells would fire 2 action potentials within this time span. That's the gray curve, and that would be at rest. If we engage the parasympathetic system, it becomes harder to depolarize the cell, and it becomes harder to fire an action potential. So in that same span of time, with the parasympathetic system involved, we only fire 1 action potential. On the flip side of that, in the same span, if we involve the sympathetic system predominantly, we're going to increase the rate of spontaneous depolarization. It's going to become easier and more favorable to depolarize these cells, and we'll end up firing 3 action potentials in that same amount of time. So we can think about the balancing here, depending on if we're at rest or if we are heavily engaging the sympathetic or parasympathetic system, and how that would change the overall heart rate by way of changing the firing rate of the SA nodal cells. Okay, so that was the neural input and the autonomic nervous system. Let's shift here and talk about the hormonal input, which is pretty much similar, right? The only difference between the neural input and the hormonal input is the route and the substance that is being used. So it's still epinephrine. Whether it's epinephrine at the neuroeffector junction as a neurotransmitter or epinephrine in the blood as a hormone, it's going to have the same exact effect on the SA nodal cells as we described in the neural regulation, right? The method is just going to be different, but the same exact effect. That is to increase the firing rate of the SA nodal cells, excuse me, or to increase the velocity of the action potential, how fast those action potentials are coming in. Okay. And then another hormone that can play a role is glucagon. So glucagon can also increase the heart rate. And we talked about glucagon when we looked at the fasted state. And so that would be a part of the sympathetic response that would increase the heart rate as well. Now, when we integrate the heart rate control, this is really that comparative secrecy that we discussed when we look at the autonomic nervous system. So sympathetic system will raise the heart rate, parasympathetic system will lower the heart rate, and any circulating epinephrine as a hormone will also raise the heart rate. So the SA nodal cells have many different inputs that are coming into them, be it the postganglionic neurons and neurotransmitters, the hormones that are coming in. And so they're going to take all of those messages, and that is how we're going to get the final heart rate by sort of adding all of the different signals that are either trying to increase or decrease respectively.